Yeah. Okay. So we have started the single electron transistor yesterday. Let me switch on my PPT. Yeah. So we have started single electron transistor. My handwriting is not very good and it becomes worse because I can't optimize my pen, so I can't see my by seeing my digital pad I can't write. I am looking at the moment to my desktop screen and writing, so often I mean it becomes very bad because I can't see my pen and write. I'm just looking at this dot and writing it. Okay. So we have been discussing single electron transistor. The important point I mentioned yesterday is single electron transistor might be useful in future because in single electron transistor we can control the motion of electron, even a single electron, by applying voltage. Okay. And I did mention that if it is found that if we have a quantum island or a very tiny nanoparticle which can be considered as a quantum island or nano island, then if we try to probe that island, okay, then the probe and the island in between there can be considered a capacitor which is very tiny. That capacitor, if it is of the order of autofarad, say 10 to the power minus 18 farad or even lower, then in that case we need to apply appreciable amount of or reasonable amount of energy to transfer even a single electron. Okay. So say suppose I have two contacts at the two ends of that nanoparticle or quantum dot. Okay. And that two contacts, there is a nano gap between that nanoparticle and the dot and the contacts. So that nano gap can act as a capacitor. Okay. And if the capacitor is really small, then you have to apply certain amount of energy to transfer electron from one contact to that island and then from island to another contact. So you see, you have to apply a specific amount of energy which is large enough to control, so that we can control the flow of electron, even a single electron. Okay. And we have shown this particular voltage which is required is known as is value of the order of should be greater than QE over 2C. Okay. So this QE is the charge of the electron and C is the capacitor value. Okay. And this voltage you need to apply more than this so that you can transfer electron. Okay. So this is known as Coulomb blockade, and corresponding energy obviously will be Q E into V, that is Q E square over 2C. Okay. So the corresponding energy you need is basically Q E square over 2C. Okay, so this is the charging energy of the capacitor. So we can plot I over V, and so you need voltage of this magnitude to get to transfer electron. So this is known as Coulomb blockade. Okay, and we have seen that the capacitor needs to be very tiny, of the order of autofarad or so that the corresponding energy, yesterday you remember we need of the order of 0.7 electron volt or that value, right? Now, so this charging energy is very low, to be honest. Okay, even if this capacitor is very tiny, this charging energy is very low, right? Now you know that what is the thermal energy? Thermal energy is Boltzmann constant multiplied by T. So kBT is the thermal energy. So often this thermal energy is good enough for electrons to tunnel. Okay, often this thermal energy is good enough to tunnel through a capacitor. Okay, if the capacitor is tiny, the thermal energy kBT is good enough for the electron to tunnel. So if that is the case, then it will be difficult for us to control the movement of electron. So for large value of C, to get Coulomb blockade effect, okay, one needs to carry out the experiment at much lower temperature, right? Much lower T. So what is that T? So Q, what I want to mean is this is the charging energy. Okay, so that has to be more than kBT, much more than kBT, so that you can effectively see that energy. Otherwise, this thermal energy is good enough to allow the electron to tunnel through this tiny capacitor, right? Now if you put some value, so C will be much less than Q square by 2 kBT, right? So this C, if C is say I can put some number, it is there in my note, say 10 to the power minus 19 farad, okay, 1.1 into 10 to the power minus 19 farad, that will give you T less than almost 8400 K, okay, Kelvin. Now if C is 1.1 into 10 to the power minus 13 farad, in that case T is 8.432 millikelvin. So you see, C has to be very small to see this effect, okay, or to control even a single electron at this temperature. Okay, so hence for larger values of C, Coulomb blockade is not visible. You can't see Coulomb blockade for larger values of C. Okay, say for this case. For smaller values of C, you can see it at room temperature. Okay, even at room temperature. For larger values of C, you have to reduce the temperature quite a lot to see. For example, you have to reduce the temperature to below 8 millikelvin to see this Coulomb blockade effect, or to control the motion of single electron. Okay, so what about the dimensions? Dimensions we did mention, we did try to show you yesterday, but dimension we can just now put again those number. So this is what we saw in the last page. C much less than Q square over 2 kBT, right? So this, if you put, say this is a parallel plate capacitor, if I consider that, okay, again you can put some number, okay, and this Q square over 2 kBT, if T is at room temperature, is around 3.57 10 to the power minus 7, okay, with you bring you consider epsilon as epsilon naught, okay, in that case. So you sorry, I again I put this number, right? So this will be this. Now, so this is at room temperature and epsilon naught considering. So you can I mean we can put again some number, maybe the capacitor plate of length L, say, so A is say L square, and maybe D I am assuming it, I am assuming D say L by 10. Okay, I am just showing you some number. Then you see you will get L square over L by 10. 3.57 10 to the power minus 7, and L, it turns out to be say around 35 nanometer. Okay, so you see you have like 35 nanometer square plate and 3.5 nanometer separation will give you some will give you opportunity to see Coulomb blockade at room temperature, right? Now the thing is, electrons tunnel through the barrier, then there is electrostatic energy. We told you that is q square over 2c. Now if there is n electron is tunneling instead of one electron, if it is n electron, then you see it will be, so again I am looking at my screen and I am drawing it in a separate place. So sorry about that. So E is equal to, we know that QE square over 2C, right? So if I consider n number of electrons, if I consider n number of electrons, so n QE over 2C, okay, say it is equal to kBT, that is the thermal energy, right? So from there you can find out the value of n, okay. So again, if you put C, KB, T, etc., etc., you can find out n. For example, if C is 1 femtofarad, say, okay, then n will be of the order of say 17 electrons. If you put those numbers, you will see that then n will be 17 electrons. On the other hand, if C is 7 autofarad, n will be of the order of 1 electron. So you see that in the autofarad range, you can literally control even a single electron at room temperature. Okay. Now the thing is, if this capacitor is so tiny and even the separation between the two plates is so tiny, then it is possible that electrons might be delocalized. Electrons might, the presence of electrons might overlap between the two plates, you see, okay. So electrons will be delocalized, and thus electron is spread over the entire capacitor. It doesn't reside on either one of the conductor plate, but it is over both the conductors, right? Now you remember, so it's kind of a tunnel junction, and tunnel junction is a, if it is like, if we can't control even a single electron, then at room temperature, electrons will be leaking from one plate to another. So it is kind of a leaky capacitor. So we are familiar with leaky capacitor when we talked about lumped capacitors, right? In our electrical study, electrical concept, we always talk about capacitors and leakage resistance associated with capacitors. You remember, we put a ideal capacitor in parallel with a leakage resistance, right? And we considered that the ideal capacitor will hold the charge, and then through that leakage resistance, the charge will be reduced or degrade or decrease, right? Or the discharging will take place. So here also, this kind of capacitor we can model, okay, this kind of tiny capacitor we can model, where we have parallel plate capacitor, ideal parallel plate capacitor with a resistor RT. So we will have a parallel plate capacitor with a resistor RT. What is RT? RT is nothing but this is a resistance which allows electron to cross the insulating junction as discrete event. Okay, so this is my ideal, where is the cursor? Yeah, this is my ideal capacitor and a parallel leakage resistor. So RT should be large enough to prevent delocalization. Okay, otherwise, like, we don't know where the electrons are sitting, whether it is sitting in the positive plate or the negative plate. Okay, because the capacitor is very tiny, the plates are very close together. Okay, so RT should be large enough to prevent the delocalization over the capacitor plate, and RT should be small enough, okay, or should not be too large. Let's put it this way, should not be too large. Okay, should not be too large, so that tunneling is possible. Okay, so if it is if it is very small, then tunneling will occur. Okay, or delocalization will occur. If RT should be not too large, okay, so that tunneling is possible. So when this is maintained, then the charge or the on the island is well quantized. Okay, charge on the island will be well quantized. Now, so it is possible to quantify this RT, okay, or this leakage resistance. And this quantification can be done. I mean, I haven't discussed uncertainty principle, Heisenberg's uncertainty principle, but you probably have come across Heisenberg's uncertainty principle, and it is possible to show that according to Heisenberg's uncertainty principle, delta E, delta T is of the order of h over 2, where delta T is equal to RTC. Okay, so if you use that, we will get RT over HQE square. Okay, you put RTC here in place of delta T, and you bring C here, and you can replace this with this formula, and it will be around 25.8 kilo. Okay, 25.8 kilo. So this H over QE square is known as quantum resistance. This is actually usually denoted as R naught, and this is quantum resistance. So if RT is much greater than R naught, then tunneling will be difficult. If RT is much less than R naught, there will be too much tunneling. So there should be a balance. Okay, the way we represent such or symbolize such quantum capacitors, okay, or such nano capacitors which shows quantum behavior or Coulomb blockade effect is in this fashion. Okay, so TJ stands for tunnel junction. So this is a symbolic representation of such tunnel junction which shows Coulomb blockade effect. Okay, now let's go back to the design which we have started yesterday. Okay, what was the design? Design was, we have a quantum dot or a very tiny quantum nanoparticle. We have two contacts very close to that of the quantum dot, right, or two probes, and we have applied a bias voltage, right. So this can be represented as as you see, we have now established a, so this is our one quantum junction, say TJA, and there is a quantum dot QD. So this is my quantum dot, or say tiny, very tiny nanoparticle, and there is another junction, say TJB, because you see there are two junctions, one junction here and another junction here. Okay, so this is say VA plus, and this is say VB plus minus. Okay, so this is basically the diagram we started yesterday. Now all we are trying to do is to see how we can control the single electron through such circuit. Okay, so we will do similar sort of we'll try to find out similar sort of expression. For example, yesterday you remember, I don't have that PPT with me right now, I mean it is in the folder, so or I have uploaded yesterday, right, in MS Team. What we did, you remember, we find out Coulomb blockade voltage, we find out corresponding energy. Okay, initial energy, then a charge or the electron will transfer, we find out final energy, then we you remember we establish that if it is energetically favorable, so higher it should, the system should go from higher energy to lower energy, so in a EI minus EF should be greater than 0, and from there we achieve a condition that gives us Coulomb blockade effect, right? So in this particular circuit also we will do the same. We will find out the stored energy. We will find out if an electron move from here to here, and then from quantum dot to this next junction, then only a current will establish, right? So far whatever we have discussed like yesterday we have discussed, like if we have a capacitor, and if one electron is going from negative terminal to positive terminal or vice versa, okay, so what is the amount of energy? Initial stored energy is EI, you remember, and then there is final energy EF, and all we did EI over EI minus EF. Just give me a second. So sorry about that. So all we did, we find out EI and EF, and EI minus EF we said, if you follow yesterday's class, should be greater than 0, because an event will only occur if it is energetically supportive, or from higher energy to lower energy it will flow, it will go, right, any event. So the same thing we will do, but instead of a single capacitor, what we will do, we will have a quantum dot, okay, because all we are interested in to find out how a single electron can go from this contact to here and from here to this contact, so that a current is established. For a current we will have to have a closed path, otherwise there will be no current, right? So if the electron only moves from this contact to QD, there will be no current. It has to be from here to here and then from here to here, right, or other way around, then only you will have current. So we will see the condition of current. That is the whole purpose of this mathematical exercise what I am going to do. I'm sorry, there is a bit of a mathematics. If you can't follow, you should also again go back to the note which I have uploaded yesterday. It is not very difficult, but I encourage you to go through those stepwise, just to understand and appreciate what is the condition when this current will establish and we will be able to control a single electron through this circuit, right? So we will follow the similar thing, exactly that basic thing what we did yesterday. So the only difference is here you see there are two capacitors. One is this TJA, one capacitor, and there is another capacitor TJB. So this is our A junction, this is our B junction, right? Now the thing is, let's write the capacitors and relationship between capacitors and charge and voltage, right? All these are known to you. Okay, so I'm tempted to write these big formulas. Please excuse me, because I mean, otherwise it is very difficult to convey the thing. But I don't want you to derive this in the exam. That is not the goal. The goal is you should understand how the things are progressing. You don't have to memorize it, but try to follow what I am doing. So you see, this is the charge associated with tunnel junction 1 and tunnel junction 2, because those two are capacitors. Okay, and there is a quantum dot. Now the thing is, if we consider net charge in the island is the difference. Okay, so net charge in the island, sorry about this, net charge of sorry about this, in the island Q equal to, say, QB minus QA. Yeah, you can consider QA minus QB also. Say, for the timing, I'm assuming net is, so charge here is QB, charge here is QA, net charge in the island or in the quantum dot is QB minus QA. Okay, and electron tunnel allows in discrete number, right? So of electrons to accumulate in the island. So this Q I am considering as NQE. So QE is the charge of a single electron. There are n number of electrons present in the quantum dot, say, at any instant or initially. So that is NQE, right? So charge is stored in the capacitor. What is the charge stored? We know that is Q square over 2C, right? So we have to write 2Ca plus QB square over 2Cb, right? So that's the charge stored in the capacitor, right? So you can also write half Ca Va square plus half Cb Vb square. Okay. Now total voltage Vs is basically divided into two parts, right? Va and Vb. So we can write Vs equal to Va plus Vb, and we can write in terms of Va or in terms of Vb. Okay, so this is Va plus Q plus QA Cb, and this Va plus Q is NQE and QA is CA Va, okay, over Cb. So if you so all these are present in the note. You just follow my steps, what I am doing. So that will help you when you will see the note. Okay, so Vs can be written as Va 1 plus Ca over Cb plus NQE over Cb. So what I am writing in terms of Va and Vb, you see, because those are not known to me. Vs is known, okay, but Va is not known. So this is one equation, right? What is another and what is Cs? Cs is, say, Ca plus Cb. Okay, so if you just simplify it, you will end up with this equation. Similarly, we can write Vb again in terms of Vsca plus NQE. So if you follow the exactly, instead of putting Va here, if you try to find in terms of Vb, you will end up with this expression. So this is one expression, this is another expression, Va and Vb. So all I am doing, you remember yesterday what I did? We find out stored energy, na? We find out you said we find out stored energy EI and EF yesterday. So that is exactly what I am doing. Okay, so I am finding out EI and EF. So this is the voltage. These two are the voltage at the two capacitors. Where are the two capacitor? One capacitor is here, there is quantum dot, then there is another capacitor, right? CB and CA. So I am finding out energy in these two capacitors, right? So these two capacitors, CB and CA, I am finding out energy, right? So this energy, this stored energy is how much? This stored energy, ESE, say stored energy in the capacitor, we have already found out, right? Half Ca Va square plus half Cb Vb square. That is the stored energy, say ESE. Okay, stored energy. Now this stored energy, I can write Ca Va square plus Cb Vb square, right? So that's my stored energy. Now if you replace this Va and Vb here, Va you put here and Vb you put here. Okay, so you will end up with, I'm just skipping some steps, you will end up with this value. Right? So that's very neat and clean expression. So EAC, the stored energy in the two capacitor, is 1 over 2 CS. CS is Ca plus Cb. In the bracket CACB Vs square plus NQE whole square, right? So that's basically a clean equation, right? That is the stored energy. Now think of a situation where I am transferring one electron from, say, terminal B to the quantum dot, right? Because what I said, that I am interested in to establish a current, and that current should be because of a single electron. Okay, so electron will go from this junction to quantum dot, and then subsequently from quantum dot to that junction, or other way around. So if I can establish a current, and if that current because of a single electron, then we will develop a single electron based device. Okay, where I am controlling the flow of a single electron. So this is my stored initial energy. Okay, but for doing this, you see, for transferring this electron from here to ultimately here, junction B, through quantum dot to junction A, who will do what? This supply voltage has to do the work, right? Because it can't happen on its own. This supply voltage Vs has to do the work, right? And you can obviously you can find out that work. Okay, when electron will tunnel through the junction, the power supply must do the work. So what is the work done by the power supply? You can find out again expression, that is, say, how to do that. Say you are integrating over T Vsi dt. Okay, so that's basically V. You remember V into I is the work done. V into I is work done, right? So you do that, and you will end up with, sorry, so dq over dt. So that's basically delta q Vs. So what is this delta q? Delta q is the total charge transferred from power supply during the charging period delta t. Delta q is the charge transferred by the power supply during the time delta t, right? So that's kind of an expression. This is well understood, I guess. Now what I am, as I said, what I am doing, I have my stored energy, I have the expression of the charge, I have the expression of capacitor, and all that is known. So all I am now going to do, I will find out the final stored energy because of the transfer of an electron. Okay, and then what I will do, I will find out delta E greater than 0. Because I said yesterday that this phenomena of transferring electron is only possible if the initial energy is minus the final energy should be greater than 0. Then only it is energetically favorable. So let me do some more steps. I'm afraid you have to bear with me. So let's take the initial So that is the basic background work. So now let's take the initial number of electrons on the island is n. Okay, so let's consider initial number of electron in the island is n. Okay. Let's initial voltage at A and B is VAI and VBI. Initial voltages at junction A and B. Okay? And the corresponding charges are QAI and QBI. Right? That is the corresponding charges. So all these are at junction A and B. All these are initial. Okay. So now let one electron is tunnel from onto the island. Okay, one electron now tunnel onto the island. Okay, through junction B. As I said, like we are considering that one electron. So far we haven't considered any tunneling. You see, we have just put these charges, capacitors, find out stored energy in these capacitors. Now what we are assuming that from one this capacitor, through this capacitor one electron is tunnel to junction to this quantum island through junction B. Okay, so if one electron tunnels through junction B from through junction B to island. Okay, then what will happen? Now VAF. So VAI is the initial voltage. Because of the transfer, what will be the voltage? You remember, you see, we have already find out VA. So this is my VA. 1 by CS VSCB minus NQE. That's the equation. So VAF, what will happen? You see, N becomes N plus 1, right? N electron was there in the island. Now it becomes 1 electron extra. So it becomes N plus 1, right? So that is what I am what I am going to write. So 1 by CS, you look at this expression, 1 by CS VSCB NQE. So it is 1 by CS VSCB minus N plus 1 QE. I hope you don't have any doubt in this, right? So what is the, it can be, it, right? What about VBA? That is the voltage in junction B. That also we will write in the similar fashion. You see, 1 by CS VSCA plus NQE. So we will write 1 by CS VSCA plus N plus 1 QE. So that is nothing but VBI my plus QECS, right? So what we will do, we have this final voltage, right? And we have the initial voltage. So we have written final voltage in terms of initial voltage when one electron is transferred from junction B to the island, right? Now So let's now write W. So what is the, so we can also write in the form of, so what I will do, I will write I will find out delta AC. Okay, so we have found out EAC, that is the charge stored. We will find out final charge stored, and the difference of those two is delta AC. Okay, so is it so far? Is it okay, or should I repeat? I know it is a bit cumbersome, but is the whatever I have so far discussed, is it okay? I think you see the note, it will be more clearer. But so far whatever I have discussed, are you okay with this?
Yes.
Okay, so right, so what I am now going to do, so I have VAF and VAF, that is the final voltage at junction A, and VBF, that is the final voltage at junction B, right? We can also find out the final charges. Okay, so what is the final charge? For example, to maintain this, so maintain this as electron is moving, we can find out this final charge, say QAF. QAF is CA VAF. Okay, right? Say at junction A. So we can write CA VAI minus CA QE over CS. So you remember that VAF can be represented as VAI minus QE CS. So that is what I am doing. Okay. So again, this can be written as QAI minus CA QE CS. Right. So this is a final charge at junction A. So note that charge supplied by the voltage source is basically, it is not simply one electron. You remember in the here I have shown charge by the charge by the voltage source is delta Q Vs. That is the charge supplied, I mean the work done by the voltage source. Okay, so that's not a single electron, that is the work done by the voltage source. Okay, so this can be written as, okay, W we have already seen, work done is nothing but delta Q Vs, that is the work done. Vs is the supply voltage. So this is Vs Ca QE over Cs. What is Ca QE over Cs? That is delta Q. How this is delta Q? Because you see delta Q is equal to QAF minus QAI. And what is QAF minus QAI? You can find from here. Okay, that is Ca QE over Cs. Anyway, so that's basically my W. So you see, due to an electron tunnel through junction B onto the island, the change in total energy is delta Et. Change in total energy. That is the change, that is the charge stored, the change in the stored energy, minus work done. That's the due to electron, what is the change in total energy. So if I do that, delta Et is equal to delta Se minus W. Okay, this is all what I am interested in. Okay, so what is the change in total energy of this system? Change in total energy is delta AC. What is delta AC? That is the stored energy. You remember we find out stored energy EAC, that is basically this, in two capacitors. That is the stored energy. So when one electron will tunnel, then there will be two part of the work. One is work done by the supply voltage and another is the change in stored energy. Okay, so we have found out the stored energy. We can find out the change in stored energy, but simply writing the formula. Okay, so what we have, delta ET, okay, can be written as 1 delta AC minus W. So what is delta AC? 1 over 2 CS. CA, let me write it down quickly, then I will just go back and you will see what I have. It is simply from the earlier formula. Okay, so this minus 2CS CA CB VS square plus N plus 1 UV square minus Vs CA UV CS. Okay, how I am coming to that expression? So if you look at ESE, this is the expression, right? 1 by CS CA CB VS square N QE square. So that's basically my stored energy. Now the stored energy is changed to what? N becomes N plus 1. In the island there is one additional electron. So all I am writing this minus the entire expression with N plus 1, right? So that is what I have written. You see, this is E stored energy, earlier E stored energy, final E stored energy is with N plus 1, right? Minus the work done by the supply voltage, right? So if you do that, this has to be greater than 0 to make these things energetically favorable. You remember yesterday also we have done the similar thing. Final energy, initial energy minus final energy, energetically favorable greater than 0. Okay, so if you just simplify this expression, you will see lot of things will cancel out. Okay, and you will ultimately end up with the similar expression we got yesterday. Sorry, similar expression we got yesterday. So this is the expression we will get when you simplify this, where Vs should be greater than QE over CA N plus half. Okay, in a similar way, when an electron tunnel off from the island through junction A. So far what I have done, this is my quantum dot, this is one island, that is TJA, there is another island, this is TJB, right? So far we have considered that electron tunnel from here to here. Now I am saying that electron will tunnel from here to here. You remember, for having current we need a closed loop. So this first condition is electron tunnel from junction A to quantum dot. If now we have another situation where electron will tunnel from QD to junction A, we can achieve similar expression, where what I have to do, we have to consider, instead of N plus 1 we have to consider N minus 1. Right, here we have considered N plus 1, right? Now if the electron tunnel from quantum dot to junction A, then the number of electron will lose. So instead of N, we have to write N minus 1, and it is possible to show, I am just skipping those steps, you will see in the note, we ultimately will get, if we follow this second case, we will ultimately get Vs greater than QE over CB N minus half. Okay, so here I am stopping today. So the two expression we got, one is Vs greater than QE CB over N minus half. Okay, and another expression we got, Vs greater than minus QE over CA N plus half. Okay, there is a minus sign, I can't remember whether I put, I put it, right? So you see, these two are the expression where it will define, that the electron tunnel from junction B to quantum dot and then from quantum dot to junction A. Okay, so then we will establish a current. We have some interesting observation through this formula that I will discuss in the next class. Okay, but please don't get scared by seeing all this expression. I think those expressions are pretty self-explanatory. You see the note and follow the steps. I'm repeating, you don't have to memorize anything. I will not ask you to prove these in the exam, but you see and try to follow the steps so that the conclusion or observation we will make in the next class will be interesting for you. Okay, so thank you very much. If you have any doubt, please raise your hand and we can then take up some questions. You don't have any doubt? If you don't have doubt, then it means two things. One, you are not understanding, or second is,
Sir.
Yeah.
Sir, how it is working as a transistor?
So that I haven't come yet. So when it will be transistor, then I have a gate terminal here. That we will discuss in the next class. Okay. So then in that case we will have a gate terminal here, and then we will see through that gate terminal we can control the flow of electron. Right?
This circuit is equivalent to diode then.
I mean, not exactly. I mean, we will see that we can pass current in the opposite direction also, and we will see that these inequalities Vs greater than something. Okay, these inequalities will give rise to some interesting current voltage expression, and you will see that current is not linear. Current will follow some staircase relationship. Okay, and we will find that for some voltages we will not be able to pass current, and for some voltages it is very easy to pass current. Those things we will see in the next class. So to be honest, it is not exactly diode, because we can have like current in both direction. Whatever things I have just discussed, we can have similar discussion where we can start with that the current is tunnel from A to junction A to the quantum dot and quantum dot to junction B, and get the similar sort of expression. So it is not a diode, but the full thing will be understood. You are right. When we add a third terminal, which is basically gate terminal, and apply a voltage at the gate, and we will see that by applying voltage at the gate we can change the energy levels in the quantum dot and make things easier or difficult for the electron to tunnel from one junction to that quantum dot. Okay, so by applying voltage at the gate we can control the electron flow.
Okay, sir.
Yeah. Okay, so if you don't have any more question, I am stopping it here today. Okay, thank you very much.
Sir?
Yeah.
Sir, in case end semester examination will happen offline, sir, then the syllabus will be whatever we had covered after mid-sem, then syllabus will be like that, no?
Usually we have in NSEM we have the entire syllabus. In practice, what happens in all earlier semesters. But you remind me after few classes, then we will take a call. Okay, we
Yes,
might
sir.
reduce the entire thing, but there will be some portion from the earlier thing also, because I think it's already 8th of March. I'm not seeing that there will be too many classes, so I might have to take some portion from the mid-sem before the mid-sem also. Okay.
Yes, sir. Actually, sir, majority of the students are sir, traveling to campus, so some time will get wasted for that. Like I'm from Uttar Pradesh, sir. It will take 24 hours for me to travel to Kharagpur. So, sir, during that time, some time will be wasted. So, sir, it will be better if syllabus will be on the lighter end.
No, okay, so that we will take a note, but if I just take like after mid-sem, then the amount of syllabus will be very, very small. So that is what I'm saying, that I have to consider at least some part before mid-sem, if not the full one. Okay.
Yes, sir. Thank you, sir.